And then our last presenter for today is Fatemeh Salboukh from University of Massachusetts at Dartmouth.
Good afternoon, everyone. I'm Fatemeh, and today I'll be presenting our work on enhancing the multiple regression-based resilience model prediction with transfer function. Thanks to my co-authors, Priscilla Silva, my advisor, Professor Fiondella, and Mindy Hotchkiss. As a quick introduction of the topic that I'm going to talk about today, I will start with the definition of the resilience, which is about creating and maintaining a system that can efficiently handle the disruption. The resilience concept varies across the domains, but it generally measures how well the system performs under the stresses and achieves its goals compared to its performance in a standard situation. Previous studies typically take the discrete model based on linear regression to predict change in system affected by one or more shocks. But as a contribution, we took an advanced form of the time series modeling, the transfer function, that allows us dynamic analysis across the variables during the different times. So, to make it more clear that the motivation of our research is about the fact that lack of resilience is dangerous. And I show you through a high-profile incident that happened in 2013. USS Guardian grounding incident that caused by ship's digital navigation systems error and caused lots of financial and environmental costs, like around 2,000 square meters of coral destroyed, loss of the USS Guardian as the ship had to dismantle to be removed from the reef, and millions of the dollars damage to the ship and the environment. So this is a quick review of the model that I mentioned that previous studies took in regression with interaction. In this formula, delta P shows the change in the performance at time t. Beta 0 is the intercept of the model. Beta I are the coefficients for the individual predictor variables, and xi are the predictor variables at time t. Beta ij are the coefficients for the interaction terms between the predictors, and the epsilon is the error term capturing the random variability not explained by the model. And the model that we employed, the transfer function, again, we have the delta P, which is the change in performance at time t. The omega and the delta here are the numerator and denominator factors, or the polynomials, and capital B is a backshift operator. XR here again are the predictor variables and at time t with a d lag, and theta and phi are the autoregressive and moving average part of the model error term. And the ET here is the white noise, or the random error, in which the ET follows a normal distribution of the 0 and the sigma squared. Here, to assess the performance of our models, I brought 3 different goodness of fit measures that each one of them gives us a different side of the model. The first one, it is the root mean square error, which is the squared root of the difference between the actual data and the predicted ones across all the data. Here, n is the number of the observations, nu is the number of observations for testing, and p is the number of the model's parameter. The next one is predictive root mean squared error, the PRMSE, which is exactly the same like RMSE, but over the test portion of the data, and shows how model is powerful for predicting the unseen data. And the last one, it is R squared adjusted, which shows us how well terms fit a curve or line, but adjust for the number of the terms in the model. And of course, how much the RMSE and PRMSE are lower, the model is better, but the R squared adjusted it is the opposite, and how much we have more value, it is a better model. To evaluate the effectiveness of the resilience model, we took the 1980 US recession dataset that has 10 covariates. Okay, here is the goodness of fit measures table. The first column shows that we applied our models in 3 different data splits: 70-30, 80-20, and 90-10. And the covariates are chosen through feature engineering. Lags show the lags of the transfer function, and it is 0 for the interaction regression. The parameters are the number of the parameters that each model takes. The RMSE and PRMSE and R-square adjective are the goodness of fit measures, and we can see across all the splits the transfer function outperformed the interaction regression, and how much more data we have, and it's more available data, we have a better prediction strength. And here is a visualization of models, and we can compare them. We can see that how much we are going toward more data. We have a better performance, and in general, transfer function shows a better performance rather than interaction regression. So, to conclude, for this presentation, we brought transfer function to predict the resilience recovery, and the results were compared with the regression with the interaction. And for the future research, we are going to examine the effect of time-varying covariates to track and predict changes in system performance when subjected to multiple shocks and stresses. Thank you.